had the title, Elements of Bilocal Holography. And indeed, it's a pleasure to be here. The past 2 weeks almost, so it's great. I feel good and rejuvenated to go back to snow and teaching and all those things. So no problem, that will be easy. Okay, the topic is has to do with some very particular type of ADS CFT studies, which might be simpler than the more complex things that you have heard. So they involve typically vector models. So it's a vectorial holography, which is a term coined by Simone Biombi, because he's the one with him who gave a big contribution to that type of holography between vector models. And so vector models are simply objects which you know very well. I is 1 to n, certain n copies of a scalar, fermion, or any other field. And the relation typically in certain number of dimensions, d. And the relationship is typically with ADS theory in d+1, as you would expect. But it is a higher spin, so theory of higher spin. Yesterday we heard a very nice talk by Alde, who described some beautiful aspects of string theory. So this should be a simple theory with one rigid trajectory. Nevertheless, a lot of studies have been done through the last 10 years, and I've been just reporting on 2 particular topics, which are in these papers, are the references. So one last year, 1810, 023, 32. This is with Robert. And 2 of my students, Kenta Suzuki and Yumi Yun. And then another paper which is earlier, which deals with the SYK model, which belongs to the category of models that where this applies to 725, and that is with a subgroup of these 2, and Schmidt does, sorry. So I'm not totally sure that I'll be able to give a full review or summary of what we have studied, but maybe give you an idea and also give some idea of what does one still want to understand. There are many things one would like to understand. Luckily, they have been taught by Jeff already. There was a talk on this SYK model, which is d=1. So let me start with d=1, and then I'll make, which is the second paper, so SYK. So d=1 might be the simplest example, although as you will see, it is fairly, the model, the SYK is fairly complex itself. The fact that it's a d=1 theory, it doesn't mean. So Jeff has written it that we are studying this model of fermions with a random coupling. And just to expedite things, let's just remember. So that was an action, integral d tau. It was an Euclidean theory which is being studied. And there are fermions psi I. And this is just to assure the Majorana commutation relations. It's a kinetic term for the Poisson structure. And then there was the Hamiltonian, which was the random coupling, IJKL. Integral over time. I will just move that integral here. You will see why, just to save time. I'm not double counting integrals. So all those are at the same time, t. not easy to write with this oscillating board. That's I didn't appreciate that. One should practice. Jeff, you did very well.
Okay.
Okay. Okay. Psi, I, J, K, L. They are all at T. And what happens with that random coupling? You essentially add the Gaussian to this. J, I, J, K, L, J, I, J, K, L, and divide by 4 or something, and there's a strength of Gaussian, which is 1 over J squared, which I will not write. But in this limit of replica symmetry, which I will not go into, which is relevant, but not for this phase of the model that people have studied, it's very trivial to say integrate out the random variable J. That just means that you solve the equation of motion, and instead of that, you multiply that with the same thing. That's the solution of the equation. So you have an integral d tau prime, and the same. Psi, 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 psi. But all these psi's are now, while these are at t, and these are then at t prime. And you begin to see what the title is by local objects, so immediately they immediately show their face, because of the indices I contracts with I. This is at time t, this is at time t prime. So very quickly you replace this action by purely by local action. And the secret of this approach to holography is a composite field, and this will be across all dimensions. This will be general. You'll be studying the dynamics of this composite field, phi I of x1, mu, phi I of x2 mu. This is just one example of something we call collective variable. It's a composite non-local operator in the real operator sense, 1 over 1 to n. And this will really be the object which will govern everything. Some kind of master field whose dynamics, if we understand it fully, we like to say that then that translates into understanding fully this theory. So that's the roughly the idea. In this case, you will just have by local in time. I will use t now, even though that's Euclidean time. Defined like that. The action is obviously easy to write in terms of that. It is this psi of t prime, derivative of t, and t prime is equal to t. That's the first term. The second term with strength j squared actually fairly nice. This integral over t, let me write t1 and t2 instead of t and t prime. It is this object, the bilocal, psi of t1, t2, but to the power 4. So looks like, in fact, this looks like 2-dimension 4 psi to the power 4, nothing major. But this is not the full action. You are studying the integral z trace of e to the minus v to h, which I defined already, but I performed a couple steps. And the original integral is really over chi, the Majorana fields. But there is a statement which is actually easy to prove, that this partition function can equivalently be written in terms of this variable psi, which is the bilocal. And but with a new action. And that is what we kind of call the collective action. I don't want to make a joke, which some people know. Anyway, what inspired the name? But, the collective action is the original action plus one term, trace log. And if you scale n this way, it will be convenient for later, then you will have an n here. You will have an overall n. If you introduce maybe some truth scaling also, you will have an overall n, and this trace log comes with the factor n. It will be some kind of entropy. And here is the answer. And the proof of why this is correct, and why this is correct to all orders in one over n. That's the secret of this approach. That we will be able to, we'll have an operator statement which will be correct to all orders in one over n. It's not the leading n only, but this is an exact operator duality which is valid to all orders in one over n. The reason this is true to all orders in one over n, obviously can be proven, but the simplest argument is if we, and this is the collective action. The simplest argument that this is correct is since n is here and nowhere else, that's truth scaling, the large n limit will be decided by a stationary point. The stationary point is this equation. Very easy. This is very easy. It is psi minus 1. This trace is meant trace log. In the sense of a matrix, there will be a notion of a star product. Always everything which will be constructed will involve this product, x1, x2, x2, x3, and always an integral over the intermediate point x2. So this will be a star product of A cross A or A cross B. Can be similarly defined. So when we say a trace, that's obviously a complicated object. It's a trace of a matrix, of this matrix. Okay, so it's not totally trivial, but the derivative is minus 1, and then T1, T2, plus J squared over n, psi cubed, psi of T1, T2, cubed equals 0. And if you remember Jeff's lecture, Jeff derived this equation in a much more complicated way. He looked at diagrams, and there were the Mellon diagrams, then the Schwinger-Dyson equation for those diagrams, and this is the same equation. You can turn it around to say, you could say, if Jeff has derived the equation at large n, then I will just be looking for an action which obeys that equation. You could just turn around. And this is very general for Yang-Mills theory. At the time when we introduced this kind of representation for collective fields, the main problem was Yang-Mills, which is still the main problem. And in that case, the analog of this equation is something called the Migdal-Makenko equation. And you could ask the question, what is the action which gives with band value, gives the Migdal-Makenko equation, and that action will govern the 1 over n function systematically, all orders, and in a standard way of first finding the stationary point, and then you know what to do after that. You study small fluctuations. So the method of studying all these theories is always the same. There will be always a complete set of Schwinger-Dyson equations, and there will be an action, and you will be studying that. So with this, we are almost finished with just description of the method. Now the solution, which I will go very quickly, and then we'll discuss the solution in the case of this SYK problem, which has still a lot of open features, as opposed to some of the vector models in 3 dimensions, for example. The scalar field with certain coupling will give you the Wilson-Fisher critical point, and the dual theory is Vasilyev's high spin theory, so the dual is extremely well specified and known, and then we have studied the comparison as it's always done in ADSC, FT. In this case, there is no knowledge of the dual. And in that case, there is no knowledge of the dual. Sorry, there is knowledge of the dual verbally, meaning high spin theory, but not specifically, meaning, and Nicholas is here, so I cannot say it too strongly, meaning there is high spin theory, there is no action, although Nicholas and collaborators have an action, but anyway, it's complicated. And that might be equivalent. An action is so complicated that you cannot gauge fix it, and we have still to improve upon it. So there is a question for this high spin theory. Vasilyev has an equation, but he doesn't know an action, yet he doesn't know how to gauge fix it. To, for example, the light cone gauge, which is standard in string theory. In a much simpler theory, which is string theory, people have been able to gauge fix the light cone gauge. So high spin theory does also suffers from this fact that the knowledge of it is actually very limited. We are not able to compute loops with that theory as yet. So there are a lot of questions there. Some might be answered by what I am talking about, by this bilocal formalism, and that in a way is also the thrust of this second paper. But let's continue this equal one. It's good enough to explain the ideas, so then we would just repeat many of those things. That's how I think. That's the strategy. Scaling variance is at j equal infinity. After you scale j, it will come out here. So that you will drop this term, and even this theory is very complicated to solve, meaning, for example, you cannot solve this equation as written, even though that's a large equation. You can only solve it when j is infinite. And when j is infinite, you will find psi 0 of t1, 2, which in this case, this is an example of q equal 4. And that can be generalized to other Qs, a sequence of SYK models. But this will be just 1 over T1, 2 to the power 1/2. So it's very simple in the scaling limit when you have dropped that term. That will solve this thing.
Wait, is sine versus the matrix?
What is it?
Sine inverse.
Sine inverse is the matrix inverse, and every time I write inverse here, that will be a matrix inverse, but if I write it here, that will be just 1 over the function.
Right.
So both will appear, and let me immediately point to where both will appear. Okay. To study fluctuations, you say I will do psi equal psi 0 plus psi bar. And that is beginning to expand this theory in 1 over n, because n is here. So maybe I can erase some of that and begin to discuss at least quadratic fluctuations, and we quickly, so we already reproduced what Jeff has done, and now we'll be looking at that equation that he was solving, and I think he ended up with the solution of the equation. We'll do that again, or a little bit, some just at least a comment on the solution of that equation. So you will see that this action, therefore, is equal to psi bar. Very schematically k, some kinetic term, which I will write down soon, psi bar. And even the 1 over square root of n terms to the power L. There will be a vertex of L order. All vertices will be here, because what you'll be doing is expanding that trace log of psi, and that will generate a systematic sequence of vertices. There you look as follows: psi 0, minus 1, psi bar, psi 0, minus 1, psi bar, and trace. In this case, this is the L order vertex. So there will be L terms. And it is in that sense that in this theory, and also in any other, we know all the vertices. That we compared with higher spin theory, that we know the cubic interactions, but they already don't know the quartic, even though that has been 40 years to work it out. That's something is kind of stopping that progress. Let's see. So we know all the vertices go ordered. I'll write a schematic picture for them, but let's just look at K. And this is bilocal, so if I want to represent K, usually you just take 2 points, T1, T2, and then 3. And I think Jeff has drawn this picture also, because he has been, that's why I'm basically making contact with him, because he had T1, T2, T3, and Fernando was upset that he doesn't permute those two, just only those two, but those two are the ones tied by this sum, 1 over n, while the other two are, so you can exchange those two and not the other two, so that's a small explanation. To go from here to there, that's psi 0 minus 1, which will be inverse of that matrix in the matrix sense. That is the word. And this is psi 0 minus 1. And here we just rescale psi, so there are 2 copies of psi. But that is essentially what this is. And so there was also another term from J squared. And I will just write 1 after normalization. Okay? So the kinetic term, so to say, the kinetic term, kinetic operator looks reversible. But as you have seen, it's not that simple. The equation K, wave function, I will use the same letter as for my field. The wave functions which you have solved is bilocal kernel, or bilocal propagator, with an eigenvalue lambda, to define the propagator. This is our standard discussion of trying to define the propagator. You have the quadratic form, you will find the eigenfunctions of that quadratic form. Then you will write the propagator with those wave functions and 1 over lambda. This is the wave functions are relatively easily defined. They are very well known in expansions in conformal partial waves, and very soon we'll be making contact with everything Fernando was saying. I will make more contact later. But the wave function psi, which has quantum numbers mu and omega, this is a 2-dimensional thing, T1, T2, so there are 2 quantum numbers of T1, T2. That's nothing but this correlator, which is often used, or delta 0. Delta 0 is basically 1/2, a very low number, T1 or T2. And this is an excited correlator operator and Fourier transform, so that you see this omega. So it will be T3, but you Fourier transform in T3 and mu here. Okay. That's about it. We all know this correlator. I want to write it down. It is 1 over T1 power h, T23 to the power h, and T12 to the power delta 0, 2 delta zeros, minus h. So that's just a 3-point correlator, and it has this form in terms of powers. So that is the wave function, and that is good news. The wave function is easy. But then if you work out the eigenvalue, that is a little bit more interesting and more complicated. And you get the answer that the eigenvalue as a function of these quantum numbers mu and omega, but doesn't depend on omega, it depends only on mu. And just to set my notation straight, we all know some notation for conformal field theory that, I don't know, delta is equal to d over 2, in this case 1/2, plus mu, and that's one notation. I also call the whole thing h sometimes, delta of h would be the same thing. The eigenvalue is very interesting. It's minus 2 mu over 3 cotangent of pi mu over 2. Okay? And we'll make a quick comment on this eigenvalue. If it was a simple two-dimensional scalar field in ADS, if that kernel was the Laplacian of something like ADS, 2, where let's introduce the notation T1 plus T2, this is just trivial, is T, and T1 minus T2 is eta. I don't want to call it Z or CY, there is some issue, it makes a difference whether you call it eta or Z. And even this A is not argument. Then let's consider a Laplacian in the zeta space, two-dimensional, it is dt squared, minus, or the other way around, d eta squared. If it was this as the kinetic term, which it is not, you would have the eigenvalue to be essentially mu squared minus d over 2 squared. So it would be a very simple function. So that would lead to an eigenvalue where number is equal to mu squared. And if it was a massive field in this Laplacian, in the zeta or anti-zeta 2, which roughly are the same for our purposes at this point, this would be m squared plus 1 quotient. This would be Laplacian of a massive field, scalar of mass n in two-dimensional de Sitter space or anti-de Sitter space. That's what it would be. But this is the Laplacian we get. So you can't get a simple answer for what the spectrum of this theory is. In fact, there is also minus 1. And if you now look at where does this vanish, if you investigate where is lambda equals 0, in the propagator, that's where the poles will be. This gives you not one state, but an infinite number of states. The first answer is mu 0, which is equal to 3/2. That you can check. Everyone can check that one. But the next answer says that mu cotangent mu minus 1 is equal to 0. That's a transcendental equation, so you have to draw the picture. And I will not be able to tell you this next mu. And there is a whole sequence of mu's. And that tells you that this little theory which we have, it looks like two-dimensional, in fact begins to have a fair geometry structure, meaning it is supposed to be two-dimensional and some kind of scalar field, but it has infinitely many poles. The first pole is in fact very relevant, that kind of relates to the graviton, and that leads to something called Schwartzian, which has been then studied in details. The other poles are totally have meaning, interpretation in the sense of a dual are totally up in the air. And what I will say next will make this topic even more complicated. I did some work on simplifying this issue, what do they mean, but I also did work which Schmidt does on making this puzzle more complicated. The simplification is that this can be seen as the source, that this theory is really not a two-dimensional, but a three-dimensional theory. So you can probably guess, by Kaluza-Klein, that three-dimensional theory would have a sequence of fields of growing mass, and then you just have to account for this formula. And if you account for that formula, then you have explained the spectrum of the SYK. We have done that. So there is a two-dimensional explanation of the spectrum. Okay. But that's not the topic. This is the next topic. What will be the next topic? We might consider this then understood a little bit, the quadratic fluctuations, but that is a puzzle. And I don't know whether you can spot the puzzle. Everything I wrote down on that blackboard allows you to find the puzzle. And this is not good. And the puzzle is sufficient to make someone very excited. But today we are not excited.
Not yet.
Yeah, it's moving, and this is like being on. So, let me try to be. So I probably stop on the complexity of the spectrum, which you might think that it is a matter spectrum, and that just erase things up to here, and take some stock, and then have a puzzle, and then we solve the puzzle. The puzzle is very simple. After all, I said you are studying the Euclidean SYK, even though I call this T. But nevertheless, you're computing Z, which is trace of e to the minus beta h of this Hamiltonian, and then we are averaging over this random coupling. That's basically the model we are studying. And what you are getting is right here, but let's roughly say that you are getting this two-dimensional theory, even though that itself is up for a question. Is it really just a two-dimensional theory? Because it had a very non-linear kinetic operator that contained many poles. But here it is, minus. And let's say that we concentrate to just one of those poles, one of the fields, one of the masses, then it would be nothing like that. Something like that. It would be psi bar. I'm writing this just to bring out the puzzle. Psi bar. Okay. The puzzle obviously is the missing eye. There's an eye missing, and that should be an eye. Because, or there should be an eye here. But let's write it the way it is. You are supposed to be studying an Euclidean CFT, and you expect to get an Euclidean ADS2. Basically, that's what happens when you study Euclidean theory. Euclidean CFT, you should get an Euclidean ADS. But this is a Lorentzian theory. But it is a Lorentzian theory. It is itself, you might say, inconsistent, because such a Lorentzian theory should have an eye. But nevertheless, this is what you get. This was derived. This equals that. There's no way out of that. And just don't tell me that you will take t to it as the usual continuation, because you see this is a bilocal. If you take t to it, that requires that you are not in charge of, David was in charge of making continuations, but in this case, he's not in charge. If you continue the original time to it, that means you should take t to it and eta to it. So you do not win. And that says you are stuck with this. This is a bilocal. So you are stuck with it. So that is the slight puzzle. The puzzle is even greater if you ask the question, what are those wave functions which I wrote down, which Jeff also wrote down? Those are very strange wave functions. They are not wave functions of Euclidean ADS space. So that tells you also, this is just the beginning of stating the puzzle and why you should be a little bit worried. But the wave functions are very strange for an Euclidean ADS space. But this puzzle has a general resolution in bilocal holography, and it's very, very simple resolution. It says basically in general that if I have this field psi x1 nu, x2 nu now in any dimension, and then whether you add this together and create a center of mass of this dipole, and x1 minus x2, as I did over there, you can call it a meter. Whatever you do, this is not a nice space-time. This doesn't look like a recognizable space-time. It doesn't. The question of metric on this space is not up for grabs. So it doesn't look like a space-time. So, and the topic is resolved by the fact that there is, you expect a field, higher spin field, in x mu z is the axial dimension, you may guess that's the radial dimension. And there are a lot of internal dimensions which characterize the spin. I will just call them theta. This would be a typical field in ADS space-time. And there is a transform between the two. They are related. And, these variables and those variables are not the same. And transform between the two is not, yes?
Antal, is the right moment to say that precisely the vertices that people have been trying to compute are precisely in terms of space-time fields. And in terms of master fields,
yeah, in terms of this, and then we will have to understand how to put them into ADS space.
So the vertices is really, some people have been working mostly on vertices in space-time.
That's
not
right.
in terms of master fields. So there, they actually have, the vertices, they are also written in terms of master fields. So it is at the same level. But it doesn't mean that from this master field action.
Oh, well, what is a master field?
Yeah, it's written in 2011, the paper by Jen and myself.
Okay, since
It has been quantized.
that is my friend, I will accept it. And you also. But I'm not sure it means the same precisely as what you mean.
So you see, the issue of vertices depends in terms of which field you want to write vertices. If you want to
we'll be happy. No, we'll be happy to write vertices. Let me maybe continue, and then you will say whether it is similar in that case. Okay. My issue at this point is very kinematical. It is the fact of reconciling this description of space-time with this description of space-time. You might have such an issue also? No.
I mean, the space-time variables are there and we can get
Right.
the conventional space-time.
Okay, but let me, this is my issue at this point. That I'm trying to say that, and obviously all of you do not see this as an ADS space. And the question is, how does it relate to ADS space? And there is a nice, simple, beautiful relationship to ADS space. Okay? And it goes as follows, which I will now try to describe on this example still, but it can be generalized to many dimensions. If you look at these variables T1, T2, the bilocal in the simple space versus this ADS space, d tau squared plus dz squared over z squared. So the variables in Euclidean ADS space. These are the bilocal coordinates, and this is an Euclidean ADS too. There is a relationship between those two variables. It's very simple, and it is simple to establish, because the conformal group acts on this, and the same conformal group acts on that. The conformal group acts here as D1 plus D2, D1 plus T2 D2, T1 squared, D1 plus T2 squared D2. That is how the conformal SL2 acts. So SL acts on the bilocal space. The conformal group on the Euclidean ADS, I should know that. That's just some factors of 2. Very simple. That's d tau, tau d tau plus c dz. You probably know this. And the next one is similarly to the previous one, that we have z squared minus tau squared d tau minus, and this is 2z tau and dz. This is d tau, this is dz. Okay? And now you say, oh, I could just find the change of variables from t1, t2 to z and tau, and this would equal, so that change of variables will tell me what is the relationship between bilocal space and an ADS space. Is that okay? I misled you because there is no such change of variables. It doesn't exist. Okay? The reason it doesn't exist is that it just doesn't exist. What I should have done, which is the correct thing to do, is the opposite of what I had done. This is the coordinate space and the momenta derivatives of coordinates. If you do the opposite and write that basically as P1 plus P2 equal P, that already is one relationship in momentum space. Obviously, this is it, that's the center of mass momentum. And then you just write P1, dd P1. So everything has to be done in momentum space. And there is a change of variables in momentum space. How do we know that? Because obviously, we first tried to change the variables in coordinate space, it didn't work. And we said maybe if I do Fourier transforms of both sides, then maybe change variables in momentum space. It did work. And it actually is a fairly relevant fact. It is as important as the CAT scan, because the transform of that kind is known as the Venom Transform. So it's not a totally trivial matter, and you will benefit from that knowledge of that transform. That's the transform which you will obtain if you pursue this question. Yes?
There is an emergent ADS.
That's right. That's what we are trying to explain or derive.
What way the physics in ADS is local?
Maybe.
Is it?
If possible, yes.
Okay.
And we, for a theory, let me say it in many different ways. If you do not know anything about this physics, and you'll be happy even if you construct some which is novel. If you are possibly, probably, if you can write down a string or a high spin action which is local, that would be great. I'm not sure you can. So, so we are not necessarily insisting on locality. But to finish this, that is the way you will proceed to find. Then there is basically a change of variables from P1, P2 to P tau. And all you have to do, you already have one. This is a two-dimensional change of variables. P1, P2 is P tau, and you might say that P1 minus P2 is that PZ. That would be a good guess, but that's not true. Rather than I'll tell you the answer, which you can then check. PZ is equal to square root of P1 times P2. So just to show that we can describe that transform. So that would be the one which maps the generators of two copies into ATS generators. This is a very elementary, I don't know, quantum mechanics exam undergraduate question of relating these two versions. We do that often with angular momenta. We have the angular form of the angular momenta versus some other forms. And now let me just elaborate on this transform. So we will have the following fact, that this bilocal in Fourier space, the field phi1, phi2, is related to the ADS space, which I will call the field, or I will just call it phi script of P tau and PZ, the Fourier transform of C and tau. So these two fields are basically related. And it is a delta function, which is the kernel P of ADS is equal to P1 plus P2, as we have found here. And PZ should be that square root, but the kernel which one comes up with is the square root of PZ squared minus 4 P1 P2, which kind of contributes mostly there. So this will be the transform in momentum space, and this generalizes to higher dimensions. So it generalizes to higher spin theory. In the case of three-dimensional CFT, this will give you the sequence of higher spin fields in ADS by such a simple momentum space transform. This is not absolutely simple as it looks like. For example, you might say, why don't you write it in coordinate space, which just means do a Fourier transform of this kernel. Then what we will have here is phi of tau z. And what we'll have here is psi of T1, T2. And the kernel is a delta function of z squared minus eta squared minus tau minus t squared. Just quadratic. You're not used to that kind of kernel, but that is a very expensive kernel if you go for a CAT scan, because this is the radon transform. In momentum space, it will be just that, two-dimensional. In coordinate space, it is this. And you do Fourier transform, you can easily show. In fact, it's expensive because the inverse is not obvious, but very necessary for getting the projection back. One can discuss the inverse, but I don't have time. So the inverse is not that trivial for this transform, which is what you would need if you wanted to do the opposite. So you would need the inverse. Okay. I'm still pursuing the SYK model, and now we just stated that to see the space-time, it would be. And what this transform does is precisely what you want. It transforms dt squared minus d eta squared into c squared d tau squared plus dz squared. So I already will tell you something non-trivial, because it does transform Gaussian or Lorentzian Laplacian into an Euclidean Laplacian. But that's what we needed, because we were studying an Euclidean theory, so I say we better use this transform. It will give us a satisfactory statement that we have an Euclidean ADS. But it brings in more, and let me now make that statement, and one more statement. This is what it does to an elementary Laplacian. But if you remember those wave functions, omega, T1, T2 of ADS, which I described and which Jeff described, he described it better than me. Those are the wave functions of this bilocal, which appear as conformal partial waves, and are part of that story of the correlator. And the wave functions of an Euclidean ADS, everyone knows the wave functions of the Euclidean ADS. It is e to the high omega tau, the Bessel function mu, omega z. Those are the wave functions of Euclidean ODS. This transform relates them. So I will just write that the Venom transform of that from Euclidean space, that's how I wrote it over there, to bilocal space. You will need to do that inverse, which I didn't do, which would then be applied on the bilocal field to get this Euclidean ADS field. But there is something else. If you analyze normalized wave functions here versus normalized wave function here, you discover that this Venom transform does not map a normalized wave functions into normalized wave function. Rather, it gives you an extra factor, which I will just call a lag factor. It is actually a function of that mu, which is over there. And the upshot of the whole thing is that after we do the transform, the lag factor, we could irradiate. It is essentially gamma 3/4 minus mu divided by gamma 1/4 minus mu. And it means the following. After everything is set, the final is, okay. Now, there's a solution to this. So we leave it on the wall, I guess. Okay. So the propagator which you obtain, but that means I'm not doing well. Okay. But here is our statement then, up to now. So the dual is, I would say, Euclidean ADS. That already is a progress. We expected that naively, but we are not getting it. But at least now we are happy with that. And the propagator in this Euclidean ADS, after this transform, tau and z, looks as follows. It is this wave functions k, mu of omega z1, k mu of omega z2, divided by that eigenvalue that I had, which is a lot of holes there, but that's not the main issue. There's that eigenvalue. But on each leg, you have these gamma factors. And basically complex complication, because here mu is being integrated over the imaginary axis, that the completeness of the K functions requires that mu is imaginary and being integrated. So that would be the propagator. But there are these factors, three quarters, minus mu, and gamma 1/4 minus mu. And the complex conjugate, gamma 3/4. These are called black factors. And I guess instead of doing more formulas, I guess I would just ask people, did you ever see black factors? And did you see them, like, do they appear? Okay. They did appear previously in the so-called C=1 or D=1 matrix model, which was a matrix as a function of time. That's an old matrix model. And 2D string theory, which is a non-critical string theory. And that was one of the original dualities. It was studied around 1990 with this kind of distribution until 1995, let's say. It was the main topic then. If we had a Mandelstam conference, there would be 5 talks on that model, the C=1 and the non-critical string. It, in a way, is the preceding ADS-CFT duality, obviously. It maps a one-dimensional theory into 2D. And the same issues occurred as the ones here, so this is nothing new. But the story I told you, I already, that's an identical story from these years. Then it took a long time to, first we had only this answer. And then it took Borczynski to multiply the known answer, which Joao worked out, and myself, and so on, which was the collective answer. Borczynski supplied the lag factors, and at first I didn't like that because you say lag factors, we can always remove that by field definition. But these lag factors have poles. And then the story becomes much more interesting because the poles where these lag factors are reflect string theory. This answer actually reflected very little. It is precisely the lag factor. The lag factors are much more important than the result in itself. And it took several years to understand that. Bilocal showed in two-dimensional string theory there are states which precisely are where poles in this lag factor are. So that completed that story of mapping this collective field, matrix field, into two of these things. So played a very big role for this factor. By the way, I didn't finish the distribution. I think this is 2018. Only one person wrote a paper, and this is C. So for some reason, I don't know why, has tenure at Harvard. You can do whatever he wants. And he decided this is what he wants to do. So that is one thing. Okay? Now you might wonder whether he's a very smart person. So you might wonder why he's doing that. But the two problems are related. They have a similar structure, similar questions. Just that the dual, in this case, is very well known. It also has a black hole. We don't know whether the Lagrange exponent is. We don't know the Lagrange exponent because it is not clear value. So this model still might be worth studying. So there might be another large number of references there. But at this point, we are studying this one, the one-dimensional SYK. So if you look at what the lag factors are, and now we are summarizing our knowledge of, at least my knowledge of the spectrum, you might not want to do this transformation, which I did, because you say, I am happy having a Lorentzian theory without an eye. This is a new kind of theory, it's a new revolution in physics, that you'll have Lorentzian theories, but you will not have an eye in the parting theory. This is what we learned from the SYK. That might be the alternative. But if you agree on this transform, then you are stuck, or I don't want to call it stuck. Because what you learn now is the spectrum was that 3 halves. 1, 2, solution of the transcendental equation. That was a sequence of states which the SYK model has. But there are poles here. So we would add to this spectrum this. So I call this star states. And they are 3 halves plus 2n. When n is equal to 0, actually, this, you don't know whether this state is matter or gravity. So in that case, that is a coincidence. So there would be 2 sequences of states. One, my interpretation is that, so the dual of SYK is absolutely not known. There is very little known. But what is known is on this one, people agree, because that is the so-called zero mode, and the Schwartzian, it relates to two-dimensional gravity of Jekyll-Titan-Barn kind, which is topological. And that's a very small understanding of the full theory. So that would be the suggested spectrum of the SYK, and remains then to be seen whether so these states would be as important as the other set of states. This set of states is very visible. They are coming here from that study of the eigenvalue which Jeff described. But there are these lag factors which gives you the other set of states. I didn't have obviously time for the second to most recent paper, that's the one with Robert. Obviously, we then went to study this in 3 dimensions. I will just mention one thing, because Nicholas is here, so if I can just add one thing. Okay? In this 3D model, which can be a free scalar field theory or a free scalar field theory at its ultraviolet fixed point, I will just tell you what the quadratic K Laplacian is, which will then tell you the spectrum which you are studying in the 3D case. That K has the following form: x1 minus x2 squared, d1 squared, d2 squared. That is the Laplacian for the 3D case, for the simplest case of a free theory. And if you ask the question, what is that in terms of the generators of the conformal group, L1 plus L2, so what is the eigenvalue lambda? This is equal to K can be shown to equal the 4th Casimir plus 1/4 of the 2nd Casimir. Okay? And this has a nice spectrum, which basically says that mu minus s minus 1/2, this is now in 2 dimensions squared. It is quartic, so mu minus s, mu squared minus s plus 3 halves. That would be the eigenvalue lambda of this Casimir in the case of the simplest bilocal theory. Okay? The poles here, which tell you what the states are, there is one sequence of poles which says that mu is equal to s minus 1/2, which says that h to add 3 halves is equal to s plus 1. This knows about Plateau-Franzal theorem. These are precisely poles of the Plateau-Franzal theorem, because the Plateau-Franzal theorem has d1/2 0 cross, this was the formula Nicholas wrote. That corresponds to phi and phi. And I had phi I and phi I joined together in this bilocal. And then the Laplacian for the bilocal was this formula. It said that the representations which appear in the direct product are basically d s plus 1. has. So this Laplacian knows about. So I don't know, Nicholas, did you ever see 4 plus 1/2 squared? That's the secret behind Plateau Franzar's theorem. Fourth. Okay. Yeah.
Mistakes?
What?
What word?
That's the secret between, that would be where the poles are, which agree with the Plateau-Franzar theorem. You know, this is the Laplacian inner theory, which features, which is basically behind that Plateau-Franzar theorem. So, you know, because the pole here is precisely where you have the states, so it gives you your states, or Plateau-Franzar states. Okay. The other set of states, and that require calculation, are Stuckelberg states, which do not have physical meaning, but that you have to show in a calculation, much like Alde did, that you calculate the Witten diagram and then show that only this set of states survives in that diagram, while this are projected out. Maybe a final comment, which is as follows. The recent theories of fishnets the theory of fishnets also has this structure, it's bilocal, because you are studying traces of phi of x1, phi complex conjugate of x2. That's the observable which Kazakov and company are studying in their correlation functions of fishnets. And then if you pursue what is the spectrum, it is this transfer, it's just a deformation of this transfer. So it would be, if you look at the poles, it would be just a deformation here and find that here. So this structure is fairly general. It appears for the ultraviolet fixed point theory of 3 dimension. It then appears for the fishnet. And this is an example of simple theories. The S5K had a much more complicated form and much more complicated spectrum. Maybe just to finish, there is a scheme called kinematic space, and I don't know. Some of you might be studying that. That also, it's renaming what we call bilocal space, because it also features this space, 2 points, and bilocal. But they define a metric on this space, which basically is x1 minus x2 mu, x1 minus x2 mu, x1 minus x2 squared minus delta mu. This is some kind of a metric on this kinematic space. And the Laplacian on this space, the kinematic space, the Laplacian which they have, is equal to d1 dot d2. And then maybe x1 minus x2 squared. But this is the scalar product here. So it is very different from this Laplacian, which appeared in this bilocal theory. So I would maybe make only one comment, which would be very nice, that this is basically totally wrong. There is not an epsilon of truth, contrary to what is believed in other parts of the world. It's just wrong. Does it have any relevance to any large n study? It just postulates a metric out of blue. There is some natural reason for such metric, but no physics. It's not related to any of these large n theories. Any of these dualities, it doesn't appear in such a theory. So with that nice comment, finish. Okay, thank you.
Any questions?
was not an insight. Just you say, I'll make a change of variables, and one set of generated, much like you would make a change of coordinates. Someone gave you the isometries in two different coordinates, like Carré versus Local. You would attempt to change of coordinates to relate one to another, and then you would show it by brute force, verify. In this case, it's absolutely the same, just that you are not making the change of coordinates, but rather change of momentum. But this Laplacians are expressible either way. You can represent them in Fourier space or in coordinate space. So it's absolutely the same as standard choice of different coordinates, which you use for the same space. Just that it is now in momentum space.
Again, about the other modes, you say so. You have the tower of Antal fields.
Right.
You mentioned the other tower that.
The other tower are so-called twists. This is how they would refer to twist 2. This is twist 2. I don't have a particular insight into if this was S+1, this is S+3. So they certainly do not participate in Plato-Franz last year. And when we studied, and this is fairly non-trivial, because you see now I have a propagator which features those states. And ultimately you might say, oh, but this is wrong, high spin theory only features this. So this would be extra, that would mean this theory is not related to high spin theory. But they give zero residue when plugged into that. So the residue of this state is zero. And that was shown in our recent paper, and obviously we were very happy that that happens, because otherwise some of these things would not agree with high spin theory. So high spin theory only involves physical state, this physical state, and that's a complete set of states.
Do you think it is related to this dipole study of Ferto and Transdal? At some point we were working on this issue of dipole.
They also have twisted states and some had sort of, yeah, it might be. These are some redundant fields. Or
they had the equation was the Laplacian to the square. There's some critical mass.
oh, that it is related. Yes, you see this Laplacian is quartic. In fact, that's not yet. That issue that Laplacian is quartic has other consequences and another debate. The fact of that there is a claimed non-locality by Ronan's slide, which we don't have time to discuss. And this Laplacian helps you to avoid that theorem. So this theory would avoid that theorem because this Laplacian is quartic.
Okay, any others? Let's thank Antal. Okay, so the next talk will be in 5 minutes, so that will give us time to fix